Hello and welcome to our lab on the force of friction. Now, as we know from Newton's second law, the net force on an object or a system is equal to the system mass times the acceleration. And so we would say that acceleration times mass is equal to the net force. Now, in the case of the modified Atwood machine, which we used to study Newton's law, we found that the system mass was m1, that was the mass of the rolling cart, plus m2, which was the mass of the hanging mass that provided the net force, right, times the acceleration of the system is equal to the net force, which was the weight of the hanging mass, so that was m2 times g. And so, as it turns out, this is not really the net force though, because when we did that lab we assumed that friction was negligent. Well, sometimes you can't do that, and in fact the net force on a rolling or sliding object is going to be, in that modified Atwood situation, equal to the weight of the hanging mass minus any frictional force, force of friction. And the frictional force can be usually, the friction of the cart rolling along, or in our case, a box sliding along a track. Also, you have friction in the pulley, okay, and other things going on. But we'll just call that the frictional force. Now, let me talk about the frictional force for a moment. The frictional force is, you can determine what that is. The frictional force is simply the coefficient of friction times the normal force. And if you remember about the normal force is equal to the weight of something times cosine of theta. So you can imagine if you have something on an incline that makes the angle theta up from the horizontal, this angle theta, when theta is 0, or the incline is flat, then the normal force is just equal to the weight of the object, because cosine of 0 is 1. Now as the incline increases, theta goes up maybe to 90 degrees. At that point there's no normal force, the object just falls, and we've defined normal before as being the force perpendicular to the surface. So as cosine of theta increases to 90, cosine of 90 is equal to 0, and so the normal force goes to 0. And so at all points in between, the normal force on an object, the force perpendicular to the surface, is equal to its weight times the cosine of theta, okay, where theta is the angle of the incline. So we have the normal force multiplied by the coefficient of friction is equal to the frictional force. The coefficient of friction is a value, this is the Greek letter mu, and it just indicates the grippiness of a surface. Ice on ice has a very small mu, but sandpaper on sandpaper has a very high mu. Okay, it just indicates the grippiness. So the force of friction depends on the normal force and the coefficient of friction. So if you're able to determine the force of friction, then you can find the coefficient of friction if you know what the normal force is. And that's precisely what we're going to do in Activity 1 of today's lab. So in Activity 1, we're going to revisit the modified Atwood machine. But this time, instead of using a rolling cart, we're using a sliding box. And so the coefficient of friction between the box and the track is obviously going to be greater than the coefficient of friction between the cart and the track. So, so this is M1 in our modified Atwood setup, which I can measure with the pan balance, the mass of the box. And then for M2, the hanging mass, I'll just put this 0.1 kilogram hanging weight right there. And so I know that my net force now in the system is equal to the hanging weight minus the force of friction. And that net force is going to cause my system to accelerate, and I can measure that acceleration with the motion sensor. So bringing these equations back up, you see that all things here are known except for the force of friction, and now I can determine that force of friction using using this equation here. And from that force of friction, then I can determine what the coefficient of kinetic friction is as the block rolls down the track. Now, up to this point, we've been talking about the system mass and the system acceleration. And so what I want to do is sort of examine this sort of piece by piece. So, for example, we have the cart on the track. And actually, it's a box on a track. And let's look at the forces on it. First of all, there's M1G, the weight of the box itself. And then, equal in magnitude to that, is the normal force. Okay, so we have the gravitational force downward, and that's equal in magnitude to the normal force upward on the box. And so the box isn't going up or down, so there's no vertical net force. However, side to side it is accelerating that way, so there's a net force to our left. So here's our string and it's going down the track, so it's got some acceleration this direction. Now, so what causes that? Acceleration is caused by net force. We know that back this way is the force of friction, and so there must be a force this way greater than the force of friction in order to cause a net force to our left, and that is the force of tension in the stream. The force of tension. And so, so from that, using Newton's second law that says the sum of the forces is equal to m1 times acceleration. Sum of the forces on m1 is equal to m1a. We know the sum of the forces is equal to the force of tension minus the force of friction. And the force of friction, of course, we've sort of already determined that, right? And we know what m1 is, so m1 multiplied by a, the acceleration, the average acceleration of the cart down the track. So we can determine what the force of tension is. So that's the force of tension for the cart on the track. Now, there's another part of the system, and that's the hanging mass. So let's take a look at the hanging mass. It's a little more simple, actually. There are really only two forces at work. Here's our hanging mass, m2, and it's tied with a string. And so for m2, we can draw two forces. First of all, there's m2g, which is equal to the weight, or the gravitational force, on the mass. And then there's an upward force, which is the force of tension that's pulling upward on it. Now, you look at this and you think, well, force of tension cancels m2g, right? But that's not the case, because we notice that m2g is accelerating downward. It has an acceleration of a, which is the same as the system acceleration, of course, because everything's attached to each other. But we know that m2g, the gravitational force, is greater than the force of tension. If it weren't, this would be going at a constant velocity or not moving at all. So let's look at our sum of forces. Sum of forces, which of course is equal to m2 times a, this mass times acceleration. Our sum of forces is actually the gravitational force minus the tension force. So Fg, which is m2g, the gravitational force, minus the friction, minus the force of tension, okay, is equal to m2a. And so by using that equation, then knowing what the gravitational force is, knowing what m2a is, we can determine what the tensional force is. And so we have two different tensions in our system, the one pulling up on the hanging mass and the one dragging the box on the track. And in activity 2, we're going to sort of look at the relationship between those two values of tension in our system. Alright, there's actually an easier way to determine the coefficient of friction between the box and the track. And it's so easy you'll laugh out loud. And here's how you do it. You just take the box and give it a shove toward the motion sensor. Whoops, maybe not so easy. And so what happens there, as I graph that motion, here's what it sort of looks like. Let's say I'm making a graph of velocity versus time. Now, as I gave it a push, because I'm going toward the motion sensor, I'm giving it a negative velocity. So it started at 0, and I gave this some sort of a negative velocity here. But when I released it, it slowed down back to 0 again. And it did so, if I look at just this portion of the graph when it was slowing down back to 0, it did so at a fairly constant rate. And so what that tells me is, when I have this change in velocity, of course, you know, I can fit that with a linear curve fit, and the slope of that is acceleration. It slowed down with a constant acceleration. That tells me there is a constant force on the box to slow it to a stop. That constant force was the force of friction. So for that box, it still had the normal force and the gravitational force, the weight of the box, canceling each other, but there was a net force back this way that caused the box to come to a stop, and that force is the frictional force. So it's here's our equation. Then the frictional force is equal to, because it's our net force, it's equal to m1a. And so by determining what this value, m1a, that gives you the frictional force right off. And so using our other equations, we can determine what the coefficient of the frictional force is between the cart and the track. And so that's just a really easy method of determining the coefficient of friction. So you'll do that and compare it to the value that you found in the more complex method using the modified Atwood machine. All right, let's talk about the final activity. We want to make it interesting, so let's give yourself a theta of greater than 0. Because cosine theta is 1, what's the fun in that? So let's make an inclined track. Now, first of all, I want to take off my pulley down here so I don't hurt it. And then you see I can incline this track at an angle. I've got it set here to where a box will slide down it. Now, this angle theta, that's something I need to know. So the one way I can determine it, well, you see this meter tape? Let's say along maybe at the 50 centimeter mark of the meter tape, my height is it's around 31 centimeters. You can measure yours more accurately. Up here, at about the 100 centimeter mark, looks like my height is around 61 centimeters. And so, so for the hypotenuse here of 50, I've got a change in height of 61 minus 31 of 30 centimeters. So, that's neat. That makes a nice little 3, 4, 5 triangle here. But and so using trigonometry, hypotenuse of 50, a height of 30, I can determine what that angle theta is. So now that I know theta, now I can make a new experiment here. I'm going to slide this box down the track. And by doing so, I can measure the acceleration of the box using the motion sensor that's still at the top of the box. Alright, and let's take a look at some of the math involved in that, because it's a little different from what we've done in the first couple of activities. Alright, so we have our track, and it's on an incline of theta, and our box slides down it. So let's do a force diagram for that box. First of all, you've got the weight of the box. The gravitational force is equal to m1g. I'm still calling it m1. And then you have the normal force. The normal force. And that's equal to m1g times the cosine of theta. So that's the normal force on the box. And so as it turns out, that normal force is sort of canceled by this component of gravity that's in the same dimension as the normal force. So we've got a component of gravity that's perpendicular to the surface of the incline, and it has the same magnitude as the normal force. It has to be like that because the box is not going up into the air or down into the track. Our net force, we know, is down the track. So where does that net force come from? Well, actually, there is a component of gravity, the other component of gravity that's perpendicular to the surface is the component of gravity that's parallel to the surface of the track. So there's a parallel component of gravity here, which is m1g times sine of theta, and that component of gravity parallel to the track, right there, that's equal to m1g sine theta. That contributes to the net force. Now don't forget that we also have the force of friction. So our total net force on the box, okay, the net force is equal to, of course, the mass m1 times acceleration m1a. And so m1a is equal to the net force, which is m1g sine theta plus, or actually we'd say minus, because it's in the opposite direction, the frictional force. So m1a, mass times acceleration, is equal to the net force, which is the component of gravity on the track, m1g sine theta, minus the frictional force in the opposite direction. And knowing these other values, theta, g, m1, and acceleration, we can calculate our frictional force. And of course, our frictional force is just equal to the component, the coefficient of kinetic friction times the normal force. But remember now, the normal force is not so easy to find. Our normal force is mg cosine theta as before, but now we have some theta that's greater than 0 degrees. So this is a different method you can use to determine the coefficient of kinetic friction. And you'll compare that to the components that to the coefficients that you found in activities 1 and 2.